Hi and welcome to Equity Education, the chemistry version. Hope you are well, and today we're going to be looking at electronegativity and bonds polarity. Okay, so I'd like you to get your booklets out and we'll get started. Okay, so electronegativity and bond polarity. In reality, there are very few purely ionic and covalent compounds. A better way to describe bonds are ionic with covalent character, or covalent with ionic character. Now, for the purpose of A-levels, we don't really need to go into much more detail than that, but if you step up to university and do chemistry, then you'll start to learn about this a lot more. Okay, so in general, the greater distance between the elements on the periodic table, we're talking about from left to right, the more ionic character. You think about the periodic table. On the left hand side, generally have the metals. On the right hand side, we have the non-metals. So really, we're talking about metals and non-metals. And if we then do the opposite, so the closer the elements are together on the periodic table, the more covalent. E.g. non-metals and non-metals. That's not surprising, you probably learnt that at GCSE. Okay, so bond polarity. We'll move on to bond polarity. So in a covalent molecule, ionic character is introduced due to a term, something called electronegativity. So what is electronegativity? So electronegativity is the ability of an atom to pull electrons towards itself in a covalent bond. And I'll do a quick example here. No, actually, we'll leave it for now. We'll come back to it. And electronegativity, there are trends in the periodic table. So electronegativity decreases for an element down a group and increases across a period. This is also very important for ionization energy, which you may have seen the video too also. Okay, so as a starting point, the most electronegative element is fluorine. And just as a tip, as you go closer to the top right hand side of the periodic table, the more electronegative the element is. Okay, so we can say if there is a big difference in electronegativity, the bond becomes polar. And a polar bond has a permanent dipole. Okay, so what do we mean by this? Now I'm going to give a bit of an example. So let's use hydrogen and fluorine. So fluorine is in the top right hand corner of the periodic table, therefore it's very electronegative. Hydrogen is not, it's nowhere near. Yep, so it's not very electronegative. According to our definition, electronegativity is the ability of an atom to pull electrons towards itself in a covalent bond. Fluorine is very electronegative, hydrogen is not. If I was going to draw the electrons in this covalent bond, I might draw them in the middle. However, that's not what happens. Because fluorine is more electronegative than hydrogen, the electrons are drawn towards the fluorine atom. As the electrons are now closer to the fluorine atom, we have a delta positive charge on the fluorine, and we have a delta positive charge on the hydrogen. This means that this is now a polar molecule, because we have a permanent dipole here and a permanent dipole here, and it is also described as a polar bond. This will be more important when we come on to the organic chemistry section. Okay, moving on. So, working out electronegativity, or whether a bond is polar or not, Pauling scale of electronegativity. So Pauling gave numerical values for different elements. The greater the value, the more polar the bond. Okay, so you can see here we're given values, and what I would like you to do is determine whether the following bonds are polar. Now, just before we start that, I'm just going to say that it's not a particularly good idea just to add up the difference in electronegativity and minus them, okay? Because they're actually relative, they're not all the same. So what I would like you to do is have a go at doing this, and then as you get more used to it, just remember which bonds are polar and which bonds are not. Okay, so I will see you in a minute. Okay, so how did we get on? Right, so hydrogen-hydrogen bond, both have 2.1, so their I are non-polar. Chlorine is electronegative. Hydrogen is not very electronegative, meaning we have a polar bond. Carbon is not particularly electronegative, nor is hydrogen, so this remains non-polar. And oxygen and hydrogen, oxygen is electronegative, hydrogen is not, therefore we have a delta negative and a delta positive, and we have a polar bond. Okay, and this is just a quick look at polar bonds and polar molecules. So molecules that have polar bonds will be polar molecules if there is a non-symmetrical distribution of charge. Okay, so what do I mean by that? So let's draw something. Draw tribromomethane. Okay, so this is a symmetrical shape. However, this is a polar molecule. Well, why? And the answer is because there is a non-symmetrical distribution of charge. And to work this out, we have to look at the electronegativities of the bromine compared to the hydrogen. Bromine is much more electronegative compared to hydrogen. Therefore, the electrons will be pulled towards the bromine atoms in these covalent bonds. This means that as we go down the molecule, the electrons will shift to here, which means this part of my molecule will be delta positive. Therefore, we can have a symmetrical shape, but actually has a polar bond, and it's all to do with the non-symmetrical distribution of charge. Okay, so moving on. So molecules that are symmetrical may have polar bonds, but not be polar because there is symmetrical distribution of charge. E.g., so we would think that, let's do it right. We would think that with this molecule, because chlorine is much more electronegative than carbon, we would get polar bonds in a polar molecule. But the chlorine is pulling the electrons equally in each direction. This means that there is no overall charge, and therefore this is a non-polar molecule. I hope that makes sense. Okay, so we're talking about symmetrical shapes and non-symmetrical shapes because it does give you some idea of how to work this out. So symmetrical shapes include tetrahedral, trigonal planar, and linear. And non-symmetrical shapes, if we're talking about distribution of charge, include trigonal pyramidal, and non-linear. These are the main ones you're going to see. Okay, so next we are going to, well, you are going to answer the following questions. So, draw the shape of the following molecules: HF, CO2, NH3, CCl4, CHCl3. State which ones are polar and non-polar. And then, just as a bit of recap, draw a dot and cross diagram of N2H4 and determine whether it is a polar or non-polar molecule. Okay, so let's go through the answers quickly. So our first one, hydrogen fluoride, linear, HF. Carbon dioxide would also be linear. Ammonia would be trigonal pyramidal. Trichloromethane would be tetrahedral. And so would our following molecule. Right, so we've got linear, trigonal pyramidal, tetrahedral, and tetrahedral. State which ones are polar and non-polar. Well, we know there's a big difference in electronegativity here, so this would be polar. There isn't between here, this would be delta negative, delta positive, delta negative, but they're pulling in the same direction, the opposite different directions, therefore it would be non-polar. There is an uneven distribution of charge here, therefore this would be polar. Even though chlorine is very electronegative, we're pulling in opposite directions, so this would be non-polar. And this, because there's an uneven distribution of charge, would be polar. Okay, draw a dot and cross diagram of N2H4 and determine whether it is polar or non-polar. Right, so let's have a go at doing this. If you remember how to draw dot and cross diagrams, I'm going to just go quickly around with my nitrogen. Now it's in group 5, so it must have 5 outer electrons. Nitrogen has 1. We have 3 bonding single pairs, unpaired electrons on each of the nitrogen atoms. We have 4 hydrogens. Probably makes sense that we can bond these two up here, which means we're going to have a single bond in the middle. So this would be my dot and cross diagram. And can we work out whether it's polar or non-polar? Well, it has an uneven distribution of charge because of these lone pair of electrons on the top. Therefore, it will be polar. Okay, so hope that was useful, and I will see you next time. Bye-bye.